First, I want to show a big picture of how optics can provide for biomedical study. So this provides a ways how light can provide information when we study with an animal. Let's say this is an animal, but it can be a human in the clinic. So one thing we have to remember is nothing provides you everything, and no modality is always good for every aspect. So this one, the x-axis is penetration depth, y-axis is resolution. So the use of light is great in terms of light has a very small wavelength, which means we use the light as a ruler, and we can measure very tiny small one, even microscopic or nanoscopic range. So, however, look at this example of an animal which bears a tumor in the brain. We want to identify the size of the tumor and whether it changes and growing and the location. So then it's rather deep inside the brain. So when you use light, we could potentially identify. So you have penetration depth of pretty deep inside, like even several millimeter or deeper range you can measure. However, in terms of resolution, it's poor because you see all the light spread out like diffusely. While you can go down to see more specific. So for example, you want to see this hemodynamic changes like functional MRI, then you can see here a red and blue coded one. This means like oxy, deoxy, hemoglobin changes. You can see this asymmetric distribution, which is great. And that is a rather deeper, but you still have resolution poor. So that is a not even microscopic range, and we call them mesoscopic. So typical light we are using as a microscope. What that means is really the resolution is in a micron range. So that we call microscopy. And however, the light microscope you are using, you remember if you go to like many slides in pathology, they use light microscope to find out a lesion and diagnose disease. And they are using this tissue section. The reason is we cannot see deeper inside. So this is only less than 1 millimeter depth you can actually use for microscopy typically. And nowadays we have a more resolution. The light, visible light, has a wavelength of several hundred nanometer. That means your resolution is also about half of that, or several hundred nanometer. However, we've devised a nice tricks recently so that we can actually give even order of magnitude better resolution, such as tens of nanometer. So we can even call now not microscopy but nanoscopy. Okay? So that's great because think about the target molecule and macromolecule you are dealing with, and cells. Their size is from tens of micron to, if you look at into the organelle, the size is a 1 micron, and even the molecules can be even nanometer range. So this allows us to study them. However, you cannot see very deep, of course. So there's a pros and cons, and resolution achievable versus your penetration depth. All right, so in this, I'm trying to provide you in 1 week of a lecture for a semester, only the core concept. So here, what we want to cover is try to first understand light as electromagnetic radiation. And also in biomedical application, we want to study how light interacts with the tissue. And the basics of this light for imaging is geometric optics, so we'll cover. And then I will introduce you the world of optical microscopy and the key concepts of microscopic imaging, especially how to generate contrast, and some of more basics of when you are working and taking images for your research, the necessary a few terms and ideas as an imaging characteristics. So here is a link of nowadays a very good websites are available So many figures, I even took it from this primer. So have this link, and whenever you have some curiosity or need, you can resort to this website. So let's think about light. So light is a fascinating topic, and still we do not understand the full detail of it. So far what we understand about light. So light is an electromagnetic radiation. So when we call light, we are likely to only say the visible range over here. All right, so before actually I better to get to the actual wavelength, which is defining the regime of the light or electromagnetic wave. So we can start with our visible light, which is 400 to 700 nanometer. So that covers from RGB or rainbow colors, from longer one more reddish, shorter one more bluish. So if we go longer wavelength, such as higher than 0.7 micron up to 1 millimeter, this is called infrared radiation. So this is good. Sometimes it's used for like warming water molecules. And also 1 millimeter to 10 centimeter is called microwave range. So look at this, even several millimeter of wavelength. If you consider the microwave oven, the oven has a door, and if you look at clearly, I have actually one here. Let me take a quick look. Remember, there's a grid in microwave oven door that is a few millimeters. So you can be worried that, oh, how come microwave do not pass through this? Because their wavelengths are actually comparable to this grid. So they will not come outside of this door. So that's microwave, good for specifically exciting water molecule to heat the water molecule. And radio waves are even longer wave. The wavelengths can be a few centimeters, but even a few kilometers. Remember, this is a huge wavelength, okay? And so this is actually showing the ranges from very smaller wavelength from the light, and now we call it lower than 400 nanometer as a UV. And remember, we have learned X-ray that's ranges 10 picometer to 10 nanometer wavelength. And even below the shorter wavelength than 10 picometer, we call gamma rays. Of course, the shorter wavelength, the higher the energy, because the photon energy is defined by energy is proportional to the frequency of the light, or this is hc over lambda, because c is the speed of light, so it's inversely proportional. The shorter wavelength, the higher energy. So shorter wavelength, you can see the wavelength is converted to bacterium about 1 micron, virus about 0.1 micron or 100 nanometer range, and this atom on angstrom range and even smaller. And that's what we are dealing with, the X-rays and gamma rays. Okay, so the radio waves have very, very long wavelength. So certain AM radio, you can see they can even go through different regions in the Earth, while even shorter wavelength or higher frequency called FM radio is it can reach within a city. Okay. So here there are like important aspects of light to understand, which we call having duality. Somehow, very strangely or interestingly, the light we can consider it as a wave at the same time as a particle. We talk about this particle aspect of light when we were discussing about the sensor, optical sensor, such as photomultiplier tube and photocathode. We have to interpret the light as a photon to explain the phenomenon. But on the other hand, many times the light behaves as more like wave. So what kind of wave? This electromagnetic wave, meaning that, let's say this linearly polarized light, the electric field vertically oscillates, while simultaneously magnetic field is longitudinal, it's perpendicular. And that E M stands for the direction of propagation. So that was can be determined with wavelength and this electric magnetic field and magnetic field. So in reality, how do we generate this this electromagnetic wave? In fact, you may remember Marconi did first invented a way to generate EM wave. So using, in fact, two poles and oscillating, and that can generate this EM wave. So EM wave actually travels or propagates in direction that's oriented E cross B, and then that direction in this thumb is the propagation direction. And so electric field and magnetic fields are perpendicular and they vibrate in phase, such as you can see sinusoidal rate. And here, important parameters are amplitude, wavelength, and the frequency. And the speed of this wave can be different depending on the medium. So the speed of this light in the vacuum is called speed of light c, and which is well defined as 3 times 10 to the 8 meter per second. However, the speed will get reduced when the medium is different. So that we have defined as refractive index or index of reflection. That's the ratio between these speeds. So like if velocity is the same as c, index is 1. So most of likely in the air, the refractive index is 1. But for example, water, it's 1.33. That means speed of light is 1.33 times faster than speed of light inside the water or in a medium. So let me reiterate the spectrum of light. So we have to understand our sensors of eye are very, very limited detector to the world. So we have visible light spectrum. Of course, it's 400 to 700. And this depicts about the wavelength of the light. And I showed you like radio wave is about kilometer, microwave is about 1 centimeter order, infrared, visible, UV, X-ray, and gamma ray. So this is kind of the cartoon to show how the wavelength is changing and covers with these different objects. So EM radiation is electric and magnetic properties common to all forms of wave-like energy. And visible light, I said 0.4 to 0.7 micron. This represents very, very small spectrum portion of entire electromagnetic radiation. However, what's important is when we understand one kind of wave phenomena, that means we can understand almost all the other kinds of phenomena as well.